Sometimes time plays an important role in strategic situations. Things take step one after the other, and not only do they do, but the actors know that they will, and that influences how they behave. So the year was 1519, and Hernan Cortes, a Spaniard, was leading a flotilla of 11 boats and about 600 men about to invade a continent later to be known as America. They were vastly outnumbered and were well aware of the heavy odds they were facing. And as is famously known, as they landed, Cortes ordered that all the boats be burnt. There's some controversy whether this was done in complete coordination and agreement with his men or it was sprung on them, but either way, it's clear what the logic behind it was. Cortes knew that as they faced these daunting odds, the men would be tempted to turn back, board the boats, and flee. And by removing that option, that increased their fighting resolve going forward. And so, again, there's not only the fact that time passes between actions, but that one reasons about that fact and impacts how the strategic situation unfolds. We see it not only when there are multiple agents involved, but even in a single decision maker here. It's not only Cortes and his men, the two actors, or the two sets of actors who are somehow actions are intertwined, but even when there's a single actor, the fact that time unfolds can impact the situation. Here's another famous historical tale, in this case of Ulysses and the Sirens. Ulysses is captaining his boat and about to pass through the Straits of the Sirens, and as is commonly known, the Sirens' song are so seductive that they would cause any person, in particular Ulysses, to do things that are in his own, not in his own best interest. He would jump into the sea, he would crash the boat against the rocks. And so what he does, according to the tale, he orders all his men to first put wax in their ears so they will not be seduced by the song. He himself, who in fact wants to hear the song, knowing that he would not be able to withstand the seduction, orders his men to tie him to the mast, and should he possibly get free from the ties, to restrain him with their swords. And so it comes to pass. They sail through the strait. When he hears the siren song, he goes temporarily insane and tries to escape from the bonds and fails, and all is good. So here again is a single actor, in this case Ulysses, reasoning about the future, thinking about what will the situation be, and taking action now to impact what the strategic situation will look like in the future. To model such situations, we turn to games in extensive form, as the term is called, sometimes simply known as game trees.
We're going to look at the simplest kind of games that involve time, which are called perfect information extensive form games. So recall that normal form games model situations in which all of the players take action simultaneously. And that means that it's difficult to use them to think about cases where people really are doing something in sequence, where there's some kind of explicit time in the setting. Here we're going to look at another game representation called the extensive form, which makes the temporal structure explicit, so it allows us to think more naturally about time. There are two different kinds of extensive form games that we'll talk about in this course: perfect information extensive form and imperfect information extensive form. We'll start with the first case. Basically, they differ by whether the players are able to reason about everything the other player does, or whether sometimes they can't observe it. So A perfect information game in extensive form is defined in a way that's much more complicated than normal form games were. We need a lot more pieces to make it work. So we need all of these different pieces here. And intuitively, what's going on here is that we have a set of players, as we did before. We have a set of actions, which now is just a single set for all of the players, rather than having a different action set for everybody. And then all the rest of this stuff is going to be used to define the utility function. And in order to get to utilities, we need to think about the temporal structure of the game. So we're going to build up effectively a game tree where players take turns taking actions in the game tree, and eventually they end up at some node where the game ends, and we're going to have a utility marking that node. So let's formalize that intuition. We'll start with a set of choice nodes. So these are going to be the nodes in the tree where players take an action, where something happens. And we're going to call that set of choice nodes H. Now, to make the choice nodes work, we need to assign to a choice node all of the different actions that can be taken in that choice node. So we have a function called the action function chi, which assigns to each choice node which actions it is that are available to a player in that choice node. And we also have a player function. And the player function tells us for every choice node who it is that gets to make the choice in that node. That's the choice nodes. We have another kind of nodes, which are the nodes where the game ends. And we call these terminal nodes. So this is a different set of nodes. It's disjoint from H, and we call it Z. So this gives us all of the different nodes in our game tree. Now we need the edges in the game tree. And we build those up using the successor function. So the way the successor function works is that it's a mapping from a choice node and an action that was taken in that choice node to a new node. And that new node can be either a choice node, another choice node, or a terminal node. And what we want is that the successor function combined with the nodes defines a tree. And in order for that to happen, we need to say that there's only one way of getting to any given new node. So the way we say that formally is that for all pairs of choice nodes and for all pairs of actions that could be taken, the only way that it can be that the successor function is equal in both of those cases is if the two choice nodes were the same and the two actions were the same. So this condition means that the choice nodes form a tree, which is what we want. So now at this point, we can finally talk about what the player's utilities are in the game. And so we're going to have a utility function for every player, and it's going to assign a number to every terminal node. So for each player, for each terminal node, we're going to associate a real value, which is going to tell us how happy that player is if they end up in that terminal node. Let's look at an example. This is the sharing game that talks about a situation where a brother and a sister want to decide between each other how they're going to share $2. So they have $2 bills, and it begins with the brother saying how he proposes to divide the money. So he starts out in this first choice node here. The brother is player 1, and so he has 3 actions that he can take in the first choice node. His first action is labeled 2-0. What that means is that he keeps $2 and he gives nothing to his sister. The second action is labeled 1-1, and that means that he offers to split the money 50-50 with his sister. And the last action is labeled 0-2, and that means that he proposes to give all of the money to his sister. In each of these cases, after the brother takes his action, we transition to a new choice node where the sister gets to act. And she gets to take one of 2 actions. In each case, she has the same 2 actions. She gets to accept the offer that he made, or she gets to reject it. And the way this works is just what you would expect. So if she rejects the offer, then both of them get a payoff of 0, whereas if she accepts the offer, then both of them get the payoffs corresponding to what the brother proposed. This video is about strategies, best response, and Nash equilibrium in the perfect information extensive form. Let's look again at the sharing game, which you see here. And now, instead of just thinking about what this game models, I want to think about it in terms of strategies. So in a normal form game, it was easy to talk about pure strategies. Pure strategies were just actions. But you can see in an extensive form game, there are sort of multiple places where players get to choose different actions. And so strategies are going to need to be something a little bit more complicated. So I want to ask you to think about how many pure strategies each player has in this game. You may like to pause the video at this point and work this out for yourself before I tell you the answer. We'll start by thinking about player 1. Player 1's kind of easy because there's only one choice node for player 1 here. And so player 1 has the 3 pure strategies that you would expect, taking this action, and this action. Things are a little bit more complicated for player 2 because player 2 has 3 choice nodes. So the number of pure strategies for player 1 is actually 8 rather than 6. Player 1 has 6 different actions. But the reason that there are 8 pure strategies is that a pure strategy really is every combination of choices that player 2 could make kind of in the aggregate. So if player 2, if player 2 were to choose like this, so if player 2 was to make the decision that in this situation he would decline the offer, in this situation he would accept it, and then again in this situation he would decline it, that's one pure strategy, and that's different from this pure strategy here. And so the number of such pure strategies is 8. So now let's try to make that a bit more general. Generally speaking, a pure strategy for a player in a perfect information game completely specifies how that player would play the game for anything that could happen in the game. Specifically, it says what actions to take at every choice node that that player gets to make a decision at. So intuitively, the way I like to think about pure strategies in an extensive form game is in terms of giving instructions to another person to play the game for you. Imagine that player 2 wants to send her friend off to play the game. Then she would need to tell everything to her friend that her friend might ever need to know in order to play the game properly. And specifically, she'd have to say for every choice node that her friend might encounter, what her friend would need to do. So kind of think of a pure strategy as proxy instructions that you give to someone else to play the game for you. Then when we're counting the number of pure strategies, we really are asking how many different sets of proxy instructions is it possible to have. If we say this formally in math, the pure strategies of a player in a given perfect information extensive form game are the cross product of the action sets for that player. So if we look at the sets of actions that are available at every choice node for the player, the set of pure strategies is then the cross product of those sets across all of the choice nodes at which that player gets to make a decision. Let's do an example that is a little bit more complicated than we saw in the sharing game. So first of all, I want to ask you here to think, what are the pure strategies for player 2? Here I'm not asking you to count them, but I'm asking you actually to say what they are. And again, you may like to pause the video and think about this for both players before I give you the answer. So we'll start with player 2. Well, player 2 has 2 choice nodes, this one here and this one here. And so the pure strategies for player 2 are going to be the cross products of the action sets at each of those different choice nodes. So here they are written out. So for example, the pure strategy CF is saying that at this choice node, player 2 will play C, and at this choice node, player 2 will play F. And because they're 2 sets of size 2, there's a total of 4 pure strategies. Now for player 1, things are a little bit more interesting. What are the pure strategies for player 1? Well, again, player 1 has 2 choice nodes, this one and this one. And so again, the pure strategies for player 1 are the cross products of those two sets. So again, there are 4 pure strategies for player 1. Why is this interesting? Well, if player 1 takes this action, then player 1 knows that he will never reach this choice node because his own action has made it impossible to reach that choice node. Nevertheless, our definition of pure strategies says that the pure strategy AG is different from the pure strategy AH. So there are still 4 pure strategies for player 1 rather than 3 pure strategies. So pure strategies are a bit different in extensive form games than they were in normal form games. However, there's something great. Once we've got this new definition of pure strategies, we can actually leverage it in order to use all of our old definitions of all kinds of other concepts. So in normal form games, we defined mixed strategies as probability distributions over pure strategies. And in an extensive form game, we can use exactly the same definition word for word. A mixed strategy in an extensive form game is a probability distribution over mixed strategies. All that changes is that the underlying pure strategies themselves are different. They're now policies of what to do at every choice node in the game. Likewise, a best response in an extensive form game is a mixed strategy that maximizes expected utility given a mixed strategy profile of the other agents. So again, that's exactly the same definition we had in the normal form. Finally, Nash equilibrium is again a strategy profile in which every agent is best responding to every other agent. So all 3 of these concepts are really just the same as they were before. Now, something we might wonder is whether Nash equilibria exist, how we can reason about them. Just having the definition doesn't, of course, give us that. But there's an even tighter connection to the normal form that gives us more. And that is that we can convert an extensive form game into the normal form. And there are a couple of reasons why this is interesting. The first is because there exists a normal form game, we can leverage results we have about the normal form, like the existence of equilibrium, just by virtue of the fact that there's a corresponding game. Also, if we find it easier to reason about the normal form game, we can actually construct it and look at it rather than looking at the extensive form. So I'm going to show you how to do that conversion. Here's the extensive form game we just thought about. The conversion is actually really straightforward. Here's the corresponding normal form game. And what you'll see is we've just listed all of the pure strategies of each agent as the actions in the normal form game. So you'll remember these because we went through them before in this game already. Here are the 4 pure strategies for player 1, and here are the 4 pure strategies for player 2. Now to fill in the payoff values, what we do is we just kind of simulate play of the game. So if, for example, I wanted to figure out how to put the numbers in this cell of the game, I would look at the pure strategy BG by player 1 and the pure strategy CF by player 2. So BG means playing like this, and CF means playing like that. And then I look at what node I would actually reach in the game. And I would get down here, I'd follow the tree like that, and so I write in the number 210. And so this whole table has been filled in that way. And this is what we call the induced normal form of this extensive form game. Now, one thing to notice about this induced normal form is that it has more numbers in it than there are leaf nodes in the extensive form. You'll notice there are repetitions. So, for example, 3-8 gets repeated 4 times here, even though it only corresponds to 1 payoff value. Similarly, 8-3 gets repeated 4 times, even though it only corresponds to 1 payoff value. And that's not an accident. That's because there are 4 pure strategy profiles that lead to that same leaf node in the tree. So this can be a problem because this blow up is actually exponential. It doesn't look so bad here because the game we're looking at is very small. But as the size of the game tree grows, this blow up can be really profound. It can mean that in practice, it might be very difficult for us to write down this induced normal form. Another thing that's important to notice is that we can't always do a transformation in reverse. So you might be curious and wonder, if you give me a normal form game, can I make a perfect information extensive form game out of it? And the answer is, in general, no. this kind of special structure that you see to the game where payoffs are repeated is kind of important. And general extensive form games, general normal form games can't be turned into extensive form games. An example of that is matching pennies. Intuitively, in matching pennies, it's really important that the two players play simultaneously. And we don't really have a way of talking about two players playing simultaneously in a perfect information game, because one of the players would have to move first. The second player would then get to see that move, and there's just no way of representing a simultaneous move game like matching pennies that way. So intuitively, we shouldn't expect a transformation from matching pennies into a perfect information game. It seems like something would have to be lost there. Indeed, there's a theorem that says that every perfect information extensive form game always has at least one pure strategy Nash equilibrium. That's not something that's true in general of normal form games. Matching pennies, which we just talked about, doesn't have a pure strategy equilibrium. It's easy to see why this theorem is true. Intuitively, randomization often serves the role of confusing the other player. And there's really no reason that could ever work in a perfect information game. If player 1 randomized about this choice, player 2 would nevertheless get to see what player 1 had done. And so it can't gain us anything to have randomization in the game. That can't create the opportunity for an equilibrium that wasn't there before. So lastly, I want to look at this game and reason about what its three pure strategy equilibria are. Now, we can do this by actually looking at the game tree and trying to think about what would make sense as an equilibrium in that game. But that can be a little bit hard to do, in part because we can't quite so easily read the pure strategies off the game tree. Instead, what can be more convenient for a small game like this is to construct its its induced normal form here, which lists the pure strategies directly, and then to just reason about the pure strategies directly on this game. So let's do that. So I'll let you, again, pause the video here if you like and try to find those equilibria for yourself, and then I'll tell you what they are. So the three pure strategy equilibria are AGCF, AHCF, and BHCE. So let's talk about how we're able to see that those are equilibria. Recall, always the way that we test for a pure strategy equilibrium in a normal form game is to, for each player, check and see whether there's any deviation that would give that player greater utility. So let's, for example, look at BHCE. If player 1 was to deviate here, you can see there's no other action he could take that would give him more than 5. And similarly, if player 2 was to deviate here, you can see there's no other action she could take that would give her more than 5. In both cases, there's something that would tie, but that's OK, because a best response just says that there isn't anything better. So that confirms that this is an equilibrium. In contrast, if I looked at something like this, which I've claimed isn't an equilibrium, you can see that it isn't an equilibrium by checking for each player. So player 2 indeed can't do anything better than 10. So this is a best response. CF is a best response to BG for player 2. But on the other hand, player 1 could deviate from BG to AG and get a payoff of 3 instead of a payoff of 2. So BG is not a best response to CF for player 1, and so this is not a Nash equilibrium. And that's it for this video. Thanks.